Hi, welcome back. So in this video, I'm going to show you how to graph rational functions with holes. Okay. So here you have a rational functions, and you cannot graph this rational function using the transformation. And the reason is you notice that you have more than one variable x. You have more than one variable. Okay, and that variable is not x in the denominator. So we cannot follow the transformations. So we have to use another method. The only time you use the transformations is when you have this kind of rational function. F of x equal to a over x minus h plus k, which is another number. So you graph this kind of rational function by using transformations. You can use one way to use transformations, okay? And you notice only have one kind of variable x, which is just x in the denominator. And this case here is we have x squared in the denominator, not just x. And you have more than one variable. You have like 1, 2, 3, 4 variables in total. Or for transformation, only have one variable. Okay, so make sure you differentiate between those two kind of rational function. Okay, one there is only one variable, which is just x in the denominator. The other kind is we have multiple of variable x. Okay, so now let's continue. How would you graph this? So first, there are key features we must identify. And the first key feature you're going to identify is going to be the hole. Okay. Now, how do we identify the hole? After the hole, you're going to identify the vertical asymptote. I call it VA, and then the horizontal asymptote, which I call HA. So how do we find the hole? And the hole represents a point, an open dot on the line, on the graph of the rational function. So that given x value. I'm going to show you, if you don't understand, by the time, hopefully when I do the graphing, it will make more sense. So for this example here, to identify the hole, the first step is to factor the numerator and the denominator. So the numerator is x squared minus x. I see that there's a repeated factor, a common factor between x squared and x, which is just x, right? And then I'm going to get, whatever is the second factor, is going to be, I'm going to take x squared and divide it by x, I get x. Why? Because now x times x is x squared. Now the next one, I'm going to take the negative x and divide it by x, I get -1. So you can multiply again, x times x is x squared, x times -1 is negative x. So now the denominator I have x squared plus 3x minus 4. So I'm going to write two factor like this. Why? Because the number in front of x squared is 1. Okay, so I can do the shortcut. But again, we know how to, in case if it was a number over than 1, you have to use the long method I showed you before. Okay, so I'm just going to write x inside each factor. Then you have to, okay, ask yourself what two number multiply to -4 and add to +3. And that number is going to be the two numbers that multiply to -4 and add to +3 is going to be +4 and -1. Why? 4 times -1 is -4, and 4 plus -1 is +3. Now, we see that there is a common factor, okay? So the common factor is x minus 1, and I'm going to simplify a number divided by itself. A number divided by itself is 1, okay? And we call this is called the whole, okay? This is going to be called the whole. The factor repeated on the numerator and the denominator, we refer it to be as a whole. And what is going to be the whole here? The whole is going to be, you use a factor, the repeated factor, which is x minus 1, you set it equal to 0, and you solve for x. So you solve for x here by adding 1 on both sides, and the new equation is going to be x equal to +1. Okay? Now, Okay, how do we find the whole? Make sure you factor the numerator and denominator. And if you can see that there's a repeated factor on top and below, that factor represents the whole. Okay, so the simplified rational expression for f of x is going to be x over x plus 4. Now, I need to identify the VA, the vertical asymptote. How do I identify the vertical asymptote? Okay, the vertical asymptote is going to be the leftover denominator. So you take the leftover denominator, which is x plus 4, and you set it equal to 0, and you solve for x. Again, you have a vertical asymptote when, for the number that make the denominator equal to 0. Okay, and if I solve for x, you find out that what number we make the denominator equal to 0? It's -4. So the domain must be, the domain needs to be, is going to be all real number except -4 and as well as +1. You also have to use the second factor, even though it has been simplified. Okay, use the original one. Okay. So how would you find the horizontal asymptote? So the horizontal asymptote all depend on the degree, and I gave you 3 cases. So let's find what is the top degree and what is the bottom degree. So for the HA, you can use either the original rational function or the simplified one. Okay. So if you want, you can use the simplified. You see, you have x. So the degree on the numerator is not 0. The highest exponent of the variable x is 1. So the degree on top is 1. And what is the degree on the denominator? Again, it's also 1. And what do we notice? They are both the same. The top degree is equal to bottom degree. Okay, so when you have top degree equal to bottom degree, what we want to do, you're going to take the leading coefficients of the numerator over the denominator. So what is the leading coefficient? The leading coefficient represents the number in front of the leading terms. The leading term is x. One number is in front of x, or one number is being multiplied to the x. Again, it's not 0, but it's 1, right? There's a 1 multiplied. So you take 1 over the leading coefficient of the denominator. The number being multiplied by x is 1. It's not 0. Because 1 times x is just x. So you have 1 over 1, that's simplified to y equal to just 1. So you have a horizontal asymptote at y equal 1, and you have a vertical asymptote at x equal -4, and the whole at x equal +1. Now let's find the y-intercept. So the y-intercept represents any point on the x-axis. Okay, any point on the x-axis, what do we notice? Have what value to be equal to 0? The x or the y, the x coordinate or the y coordinate. So any point on the y-axis has what equal to 0. The x value is going to be 0. So what you need to do now, you're going to replace 0 with the x to find the y-intercept. So so basically you need to find f of 0. So I'm going to use the simplified form, the simplified rational expression. So wherever there used to be x, I'm going to use empty parentheses and plug in 0. So 0 is just 0, and 0 plus 4 is 4, and 0 divided by 4 is 0. Okay, the 0 is not in the denominator. The 0 is on top, so it's 0. So 0 divided by 4 is 0. So the y-intercept is 0, 0. So now let's move to the x-intercept. Okay, for the x-intercept, what do you want to do? Remember, if you have on the x and y coordinate grid, any point on the x-axis has what coordinate equal to 0, x or the y. If you notice, every single point doesn't have any height. So you notice that the y is 0. This time around, the y is 0. So now how do we find the y-intercept? You want to set up f of x to be equal to 0. And now for rational functions, okay, the only thing you do care, you don't really, the only thing that can be equal to 0 is not the denominator, okay? The denominator cannot be equal to 0. It's only the numerator. So I'm going to take the numerator, which is just x, and I'm going to set it equal to 0 and solve for x. Uh-oh, it's just x. X is already by itself. It's already been solved. So yeah. So the x-intercept is again 0, 0. So now let's move on to the domain and the range. So the domain represents x values. You want to look at the x values, okay? What are all the possible x values? Okay, let's look here, the original factor form here. So we notice that on the numerator, the x can be any real number. It can be any real number. There's no restriction on what x can be, okay? Because the numerator is a polynomial, okay? Now, you have a rational function, which is made of a ratio of two polynomials. Now you have so now you have to figure out what numbers we make the denominator equal to 0, because we cannot have a number divided by 0, okay? So let's say if you take 1 and you divide by 0, it's always, you divide by 0 error. So a number divided by 0 is undefined, okay? So we need to, whatever number that makes the denominator equal to 0 needs to be removed from the domain, okay? The x cannot be those numbers that will make the denominator equal to 0. So what number will make the denominator equal to 0? Is it going to be 4 and 1, 4 and negative 1? So again, it has to always be the opposite of whatever number you see. So negative 4 plus 4 add up to 0. So x cannot be equal to negative 4. Now x minus 1. So if x is positive 1, positive 1 minus 1 add up to 0. So it means that the domain is going to be all real number except what kind of number? Except the number, let me start from least to high, from negative 4 and positive 1. Now, how do I write this in interval notation? So you want to start from, let me draw a visual. This is 0. Let's say this is negative 4, this is 1. So open dot at negative 4 and 1. Why? Because you want to remove those numbers from the domain, the x values. So you're going to go from negative infinity up to negative 4. Okay. Let me zoom in. Then union, then you're going to start. So the parenthesis means skip negative 4. Okay. So now we stop at negative 4. So you're going to now start at negative 4, parenthesis at negative 4 to remove it from the domain, omit it from the domain, comma up to positive 1, close the parenthesis. So we stop there. Why? Because you don't want to include the 1, union, and then parenthesis 1, comma positive infinity. And that's the domain. Okay. So now for the range, it's going to be all the possible y values. Okay. So how do you find the range? For rational function, the range is going to be, you're going to look at the horizontal asymptote. Okay. Because the horizontal asymptote, imagine this is the y-axis. Okay, the horizontal asymptote is at 1. Let's assume this is 0 and this is 1. So you're going to have a horizontal line, okay, that pass the y-axis at 1. Okay, and you notice here what we notice about the horizontal asymptote. The rational function is going to approach it on the asymptote, but never crossing it over. Okay, so that's why you're going to have an open dot at 1. So this is a 1 here. So to find the range, you're going to go from negative infinity up to 1. So this is positive 1. Okay. Close the parenthesis. So let me write in word first. So you're going to be all real numbers except the number 1. And well, so imagine this is, let me draw the visual here again. Let's assume this is 1 here. So it's going to be an open dot. So you are going to go from always from lowest to highest, from negative infinity, comma to 1, close union, and you start at 1, comma to positive infinity. Okay, so now we have all the key features to help us graph the rational functions. So now let's do the graphing. Okay, so please graph a graph paper. I have this piece of graph paper. Okay, so I'm going to use it. Okay, before I graph, let's summarize what you've done so far. So there is a whole at x equal 1, a vertical asymptote at x equal -4, a horizontal asymptote at y equal 1. There is the x and y intercepts are located at the origin, okay, and the domain are listed here in the range, okay. So now let's plot the point, okay. Okay, so the whole I'm going to do after I'm done graphing, okay. So I know that you do have a horizontal, a vertical asymptote and -4. 1, 2, 3, 4. So let's draw the vertical asymptote first. So the first one is x equal -4. Okay, and notice also, make sure that the horizontal asymptote and the horizontal asymptote and the vertical asymptote are always going to be an equation. And I notice on your work that some of you are not using equation. You're just using numbers, and that's not correct. Okay, it's have to asymptote always is written. The asymptotes are always written as an equation with a variable and an equation. Okay, so now the horizontal asymptote is going to be y equal 1. So y equal 1 is right here. Now, next step is we're going to, okay, so we've done the vertical asymptote, the horizontal asymptote. So now the origin, so okay, so the first point you have is the origin, and it's not enough points. So what I want to do here, I'm going to evaluate. So you're going to go and evaluate the functions at x equal, let's shoot for x equal -2, okay, and see how the function behave at x equal -2 and at x equal +2, okay. So let's do that. So you're going to evaluate f of -2. And remember, there's going to be a whole at x equal +1. Okay, so I use a simplified rational expression, and then where there used to be the x, I'm going to plug in the -2, and let's compute. So -2 on the numerator, -2 plus 4 is 2, and -2 divided by 2 is -1. So when x is -2, y is -1. So let me plot that point. So when x is -2, y is -1, which is right here. Okay. So now let's do f of 2. Okay, so f of negative, when x is 2, the y value is 0.333 repeating. So it's going to be just below 0.5, a tiny bit. So I'm going to eyeball it right here. Okay, and I also evaluate f of -3. So when x is -3, is y value is also -3. So -3 is right here. Again, -1, 2, 3. Okay, so now I know that what is going to happen is and remember at 1, you have a hole. Okay, so let me use a pencil so I make sure I'm not, okay. So you're going to connect the dot using the line, and make sure that the rational function is going to have pushes on the asymptote but never crossing it over, like that. Okay, so and make sure you include the arrows at the end, always. because the line continues to go down and approaches to y equal 1. Okay, now I'm going to graph the left piece. So I'm going to evaluate, let's say f of, this is -4, -5, and then evaluate f of -7, and then evaluate f of -9. So let's do that, okay? So you're going to evaluate f of -5 and f of -7. Please pause the video and do the evaluation, okay? Okay, so I did also evaluate f of -9, and those are my coordinates. Okay, and that's the point I'm going to plot. The last 3 points I need to plot. So let's do that. So the first point is -5, comma 5. So -5 is 1, 2, 3, 4, 5. And then you have -7 is 2. And 2.3 is going to be a tiny bit below 2.5. So, and then -9 is going to be 1.8. This is 1, and 1.8, a tiny bit over 1.5 right here. Okay, so I know that the rational function is going to approach it on the asymptote by never crossing it over, like that. And make sure you connect and include the arrows at the end. Now, remember, there is a hole at x equal 1. Don't forget about the hole. So at x equal 1, that's why I use a pencil. So I am going to now use my eraser, and I'm going to erase. So we see the line. Let me zoom in so you can see what I'm trying to do. You see the line at x equal 1 on the line of the function. What I'm going to do is I'm going to draw a hole at x equal 1. So it's going to be a hole like this. Can you see my hole? Oops, sorry. Now, so at x equal 1, I drew a hole, okay? So now I can erase, maybe I'm going to use I want to use my pen since I use blue here. So now I'm going to connect by using my pen. This time around, make sure you use the hole, and then you make sure you approach. And that's it. And we are done graphing the rational functions with a hole. Okay, so I hope the video was beneficial to you and you learned a lot. Okay, so thank you for watching my video, and I appreciate you. Have a wonderful day and see you into the next video. Bye bye.